a lot of what I planned to say about the periodicity of the perturbation.
Say it again, it is complicated, say it again.
Well, I think that a good idea is that we go in more detail on the definition of the phonon, on the dynamical matrix, and on the description of the lattice dynamic of a solid in terms of phonon. So let's remind a little bit the theory. So we consider a solid and periodic solid, and we indicate with Ri the equilibrium position of the atom, where Ri is R mu, where R mu indicates the Bravais lattice, and ds is the position of the atom inside the unit cell. So we take a model of a solid composed of n unit cell that has a volume V, and omega is the volume of one unit cell. And then we okay, and n. So n unit cell, each one of volume omega gives a volume V. And on this big volume, we consider Born-Karman periodic boundary conditions. So you have to imagine to have an infinite solid where we consider a volume V of this solid, and then there are periodic conditions outside this volume V. So the displacement of the atoms are indicated with Ui, and the Ui is a function of time. Okay, within the Born-Oppenheimer approximation, Born-Oppenheimer adiabatic approximation, the nuclei moves into a potential energy that is given by the total energy of the electron system, where the position of the atoms are some parameters. For instance, we will consider density functional theory, and we will consider the energy of the electrons within density functional theory, calculated at fixed ionic positions. So we can do the usual second harmonic approximation, where we expand the total energy in a Taylor expansion of these displacements, and we stop the expansion at second order. So we assume to have a solid in equilibrium, so the first derivative of the total energy, that are the forces, are zero, and the potential, let's say, of this potential in which the nuclei moves depends on the second derivative of the total energy with respect to the displacement of the atom. So if we do the dynamics with this kind of potential, we do a classical dynamics in which we introduce the momenta, the momentum of the ions, and the kinetic energy of the ions given by p squared divided twice the mass of the atoms, and the potential energy on which these ions moves is given by this total energy of the solid expanded, or the total energy of the electron system expanded to second order in the harmonic approximation with a potential that has this form. Then, with this Hamiltonian, we can apply the Hamilton classical motion of this system that now has a number of degree of freedom that is given by the number of cells that we consider, multiplied by 3 because we have 3 Cartesian coordinates, and multiplied by the number of atoms that we have in each unit cell. So in principle, we have to solve a coupled system of equation for the displacement pattern for the displacement of each atoms that are given by the Hamilton equation. And in principle, we have this big system of differential equation to solve. So you know that this okay, if we apply this Hamilton equation, we obtain the usual equation here, where we have the second derivative of the displacement with respect to time is given by the forces that act on the system, and is given by a sum over all the atom j and all the direction vector of this second derivative of the total energy. So you know that how one can solve this kind of, can simplify this kind of system of differential equation, basically introducing the Phonon solution. So the Phonon solution means that we search we solve this system of coupled equation by assuming that in each unit cell indicated here by the index mu, that is the Bravais lattice index mu, we know the displacement in the unit cell mu. Basically, if we know the displacement in one unit cell, for instance, the unit cell indicated by mu equals 0, and then to get the displacement in the unit in all the other unit cell, we have just to multiply by a phase factor e to the q r mu, and by a time dependence that is given by a phase factor. We will take the real part of this quantity as the actual displacement of the atom. We put also the square root of the mass here in order to simplify the following equation, and we write the displacement in this form. To put the mass here is not really required, but it simplifies just the following equation. Okay, so this is the kind of displacement that form a phonon. And so our problem will simplify, and we will have many problems at a different vector q, and in each one of these problems we will have as a variable to determine the phonon displacement, the displacement of the atom S in the displacement of all the atoms in one unit cell, and the three coordinates. So if you insert this solution and you make the second derivative of the phase factor, you will obtain a square of the phase factor, and you will see that inserting this expression of the phonon and now introducing again the index u and s and mu and s prime, we end up with an equation for this displacement that are now just 3 multiplied by the number of atoms, but we have many equations for each q vector, where we have here is the dynamical matrix that is defined like this, as the second derivative of the total energy with respect to the atomic displacement of the atom in the cell mu and in the cell nu, multiplied by a phase factor that contain the difference, the distance between R mu and R nu. So you note here that here we have just a sum over mu, so over all the unit cell, while the index mu does not appear in the definition of the dynamical matrix. The reason for this is that this expression is independent on which mu we decide to take, because since these second derivative are translationally invariants, for the translational invariance of the solid, it is in influent which unit cell we take as starting the unit cell. For instance, we can take this mu as the 0 unit cell, or we can sum this expression over mu and divide by the number of cells. This will be done later. But this expression is independent from mu. Okay, so as Stefano has shown, density functional perturbation theory teach us as what we have to do to calculate the derivative of the total energy with respect to external parameters. For instance, parameter lambda, that can be a displacement of an atom in one unit cell, and also with respect to two parameters that we can call lambda and mu, that where this lambda and mu, just to fix the idea, are the displacement in one unit cell mu s alpha and the displacement in the cell mu of the atom s prime in the direction beta. You have already seen this term that Stefano has illustrated very clearly. There is a quantity that is the derivative of the charge, the response of the charge with respect to the perturbation, that we have to integrate with the response of the local potential with respect to the perturbation. There is also a term that comes from the second derivative of the local potential, actually with respect to the two parameters when we do the derivative with respect to the same atomic position. We will see later. And we have to integrate this second derivative of the local potential with the charge density. And then there is a term that comes from the ion-ion interaction that can be treated with Ewald technique, and that I will not consider in the following. So here we have an expression for derivative of the total energy with respect to two parameters, for instance, two atoms. So our question is, how do we apply this kind of formula to a phonon displacement, where we have a concerted displacement of all the atoms in all the unit cell, each one given by what happens in the first unit cell multiplied by a phase factor that brings the displacement from the original the one unit cell to all the other unit cells. So the question that I want to show you is that even if this perturbation involves in principle all the cell, and here we are doing integrals over all the cell, we can solve, we can calculate this integral in the case in which the perturbation is a phonon, doing integrals over just one unit cell. And then, with the tricks that have been in part already illustrated, we can calculate the relevant quantity to make these integrals. Not exactly this, but the one that enter in the expression of the dynamical matrix, that is this linear combination. So we need the second derivative of the total energy, and then we need to do a sum over all the unit cell with the appropriate phase factor. So I want to show you that the calculation of this term, the dynamical, that is the dynamical matrix at finite Q, can be done by calculating appropriately the two integrals that we have seen. That are the answer of density functional perturbation theory to the question what is the second derivative of the energy with respect to two parameters. So before doing this, let me also use this transparency to show just to give a derivation of a point that has been done before that possibly it can be derived here also. So the derivative of the charge density with respect to a parameter is given by this expression. So where we derive the definition of the charge density, the square modulus of the orbitals, with respect to the parameter mu, and we have to make this products of a complex conjugate of the wave function, the derivative of the complex conjugate multiplied by phi, plus the complex conjugate of this expression. We have seen that the density functional perturbation theory gives us just the projection in the conduction band of this perturbed wave function. So let's show that actually it's just this projection that enters in the definition of the charge density. Okay, we can do this. We can put a projection in the conduction band in front of the derivative of the wave function with respect to the parameter mu, and the projection in the conduction band in front of the derivative of the wave function with respect to mu. We use the fact that PC plus PV, so the projection in the conduction band plus the projection in the valence band, is equal to the identity. So if we put a projection in the conduction band here, we have to sum a projection in the valence band. So the sum of this and this term give the original derivative of the wave function star with respect to mu. And the same here, the sum of these two terms, projection in the conduction band plus valence band, gives the original expression. And now we show that this last expression here is 0. And it is 0 because if we write this valence projection as the product of another index j of C star Cj, C star j, so we have to do the scalar product of this Cj with this C over the mu, and multiply by this product of this Ci and the Cj that comes from the projector. The same thing here, we will obtain Ci star, we will obtain Ci star so Cj star d Ci over the mu. And if we exchange E with J in the second expression, we get Cj Ci, and then this scalar product of Ci and d Cj over the mu. So you see that this term is just the derivative with respect to mu of the scalar product Ci Cj, that is equal to 0 because this scalar product is the orthonormality constraint, that is delta ij, and therefore this product is 0. So just the projection, the conduction band of the change of the wave function enter in the expression of the charge density. Okay, so we have already seen that the projection of the conduction band of this change of the wave function is obtained by solving a linear system where the right-hand side is the change of the Cornish-Hahn potential with respect to the parameter mu, multiplied by the wave function projected in the conduction vector. The change of the Cornish-Hahn potential is this: the change of the local potential, the change of the Hadley potential, and of the exchange correlation potential. Okay, so now our problem is how do we apply this expression to get to the dynamical matrix at a given Q? And so I think that for this transparency, can you? Q is missing. So we have already seen the definition of the phonon. So let's return here. So the expression of the dynamical matrix that comes from the dynamical equation is this: is the second derivative of the total energy with respect to the two displacement, one in the unit cell mu and one in the unit cell nu, of the atom S in the direction alpha and of the atom S prime in the direction beta, and then this second derivative has to be done at u equals 0. So there is then this phase factor e to the iq r nu and e to the iq r nu, and the 1 divided the square root of the masses. This is the quantity that we want to calculate, and we know how to calculate the second derivative of the total energy with respect to two parameters. There is a problem here. You see that if we do the displacement of an atom in just one unit cell, we obtain a solid that is no more periodic. So it is clear that this second derivative is difficult to do. However, as Stefano has shown, if instead of moving just one atom in one unit cell, we do a concerted displacement in a phonon with the shape of a phonon, then all the responses have periodicity Q, and we will precise better what we mean. And we can calculate this dynamical matrix directly. So let's see how this works. So we have just to introduce for the second derivative of total energy with respect to two parameters the expression that we have learned from density functional theory. That is, we have the second derivative of the local potential with respect to these two parameters integrated with the charge density, and the product of the local potential, the derivative of the local potential with respect to the displacement u in the unit cell mu, multiplied by the change of the charge density in the unit cell nu when we move the atom S prime in the direction vector. The definition of the dynamical matrix tells us that we have to do a sum over mu and nu. So we put 1 divided by the number of unit cells. We have to do integrals over all the volume V at this point at least. And these integrals contain a sum over mu and nu of this phase factor with the second derivative of the potential. And here the same. We have separated the sum over mu and nu with the appropriate phase factor. So the term that we have to integrate are this kind of terms. So the change of the local potential in one unit cell nu multiplied by a phase factor minus EQR nu, and added over to all the unit cell nu. And the same thing for the charge density. We have to sum over all the cell, each one with the appropriate phase factor. So I want to show you that this integral can be done actually. It is not that this quantity is a periodic quantity. We have seen that Stefano has shown that this quantity has a periodicity. So now we try to define in more detail what do we mean by saying that it has a periodicity. So, and I want to show you that we can, defining appropriately the quantity, calculate these integrals doing integrals just in one unit cell. So, you can see this we can take as a definition of the derivative of the local potential with respect to this quantity US alpha and of Q and US prime beta of Q are the displacement in one unit cell. The one that multiplied by the phase factor give us the displacement in all the unit cells. So you can see that this definition is consistent, if you want, with the definition of the phonon, with the phonon displacement. So if we define the derivative of the local potential as this term, so as the derivative of the local potential with respect to the displacement in the cell mu and in the cell nu of the atom S in direction alpha and of the atom S prime in the direction beta, and then multiply by the phase factor, this is exactly what we obtain if we would think that the local potential is a function of the actual atomic displacement that have a unit cell index mu, and then multiply by the derivative of so we make that the derivative of V log with respect to this u, for instance, US prime beta Q, is the derivative of V log with respect to so let's say like this. V log depends on the displacement of all the atom in all the unit cell. The displacement of all the atom in all the unit cell can be determined by the definition of the phonon, by this definition. So the displacement of the atom in one unit cell are a function, depend on the displacement that we decide in one unit cell. So the derivative of a given quantity with respect to this US alpha of Q is equal to a sum over all the mu of the derivative of this quantity with respect to this displacement u mu multiplied by the derivative of u mu with respect to the US that gives the 1 divided the mass and the phase factor. So for instance here the derivative of V log with respect to US prime beta will give us a sum over mu of the derivative with respect to all the displacement nu, and the phase factor e to the iq r nu, and 1 divided by the mass m over s prime. Then the derivative with respect to u star s alpha can be done in the same way. We'll give the derivative with respect to the sum of all mu, the phase factor with a minus because we are deriving with respect to u star, and the square root of the mass. And so this expression that enters in the definition of the dynamical matrix formally can be written as a second derivative with respect to the quantity that define the phonon displacement, so the position, the displacement of the atom in one unit cell. That is the quantity that we will get by diagonalizing the dynamical matrix. So we will show in a moment that this expression is actually lattice periodic. it has to be integrated with the charge density that is lattice periodic, and so this integral can be done just in one unit cell. The other term instead, this term, contain a sum over nu of the derivative of the charge multiplied by its phase factor, and also this term can be formally written as a derivative of the charge density with respect to this displacement in one unit cell, in the zero unit cell US prime of Q, as a sum over nu of the displacement in the atom in the cell nu, and multiplied by its phase factor. So the quantity that enters in the expression of the dynamical matrix is actually the derivative of the charge density with respect to the amplitude of the phonon displacement. The same reasoning can be done for this local potential. We can define with the star, because there is the minus EQR mu, we can define the sum over mu of the two lot with respect to u as alpha, and the phase factor e to the minus alpha. Now what one can show is that both this expression of the derivative of the charge density with respect to the amplitude of the phonon, with respect to the displacement of the phonon in one unit cell, and this derivative of the local potential with respect to the displacement in one unit cell can be written as a periodic function, a function that is periodic in one unit cell, multiplied by a phase factor EQR. So there is a phase factor and a periodic function. So this object is not a periodic function, but is just a periodic function multiplied by a phase factor e to the QR. That is actually the hypothesis that Stefano used as his. So he considered what happens when the perturbation has a periodicity Q, and how you can use density function perturbation theory for a perturbation that has this type of shape. So a periodic function multiplied by a phase factor. And what he has already shown, but maybe I will repeat, one can show that actually all these phase factors do not need to be explicitly included in the calculation. They have to be accounted for, but we can work with the periodic part of the functions, so with objects that are defined in one unit cell. So if this thing is true, so we have not yet demonstrated this, but if we can demonstrate this, then our dynamical matrix is the second derivative of the local potential with respect to U star as alpha to Q, that we have. I said it is a periodic function multiplied by a periodic function, so we can write this as just one integral over one unit cell, and that's that's our goal, because we want to work in just one unit cell, not in the big volume V. But we have to keep track of this phase factor, not here because this is a periodic function, but in the second integral we will have a phase factor E minus EQR that comes from the local potential, a phase factor E to the IQR that comes from the derivative of the charge density, and these two phase factors cancel, and we can write the dynamical matrix as an integral over just one unit cell. So how do we prove that, first of all, this is a local, so it's a lattice periodic function? Well, we observe simply that the local potential is written like this, as a sum over all the atom mu and s of a potential, a local potential that depends on s, we have that we have to center this local potential in the position of the atom r mu plus ds plus u s. And then we have to make the derivative of this quantity with respect to two displacement. It is clear that if we do the derivative with respect to one of the two displacement, this will, in this sum, select just the unit cell mu, the atom s, and this displacement. So when we do the second derivative, if this mu is another cell or another atom S prime, this term will not contribute. So in this second derivative, there are just the term in which mu is equal to nu and s is equal to s prime. But if mu is equal to nu, these two phase factor cancel, because one has a minus sign and the other has a plus sign, and so we end up, and then we have also that s and s prime must be the same. So this term is actually as a delta of s and s prime, okay, one divided the mass, and then a sum over all the atom of this same quantity that is the second derivative of the local potential, each one centered in the position in which we do the second derivative. So this is simply a function that is copied, translated in all the unit cells. It's the same function, and that give rise to translated in all the unit cells give rise to a lattice periodic function. So this is clearly a lattice periodic function. To show that the change of the charge density with respect to the phonon, the phonon displacement in one unit cell is given by a periodic part multiplied by a phase factor, is not difficult. What we have to do is we calculate the Fourier transform of this object, and we show that it has components just at the vector Q plus G, where G is a reciprocal lattice vector. So it means that it will be a phase factor e to the iq multiplied by a lattice periodic function. So how do we demonstrate this? Well, we can do like this. So we calculate the Fourier transform. It's 1 divided the volume, an integral of the volume of this phase minus iqr multiplied by this quantity, so this just the same object. And now let's do a simple observation. So suppose that we move the atom S prime in the direction beta in the unit cell nu equals 0, so the unit cell close to the origin. And then we look, we probe the charge at the point R. If we do a displacement in a unit cell that is translated and that is given, so it is translated with this lattice, Bravais lattice R nu, and so we do the same displacement in the same direction and of the same atom, but in another cell. And then look at probe the charge not at the point R, but at the point translated. Since the solid is translational invariance, this derivative must be the same. So the derivative of the charge density with respect to the displacement in the unit cell given by the Bravais lattice 0, and looked at R, or the derivative with respect to the displacement in the unit cell nu, and looked at R plus R nu, these two objects must be the same, because we are just doing the same thing once close to the origin, once close to the unit cell nu. So there is no reason why these two objects gives different quantity. Now, if instead of r we take r prime equal r prime minus r nu, okay, we will have here r prime and here r prime minus r nu, and these two derivatives must be the same. So this quantity that appears in the definition of the derivative of the charge with respect to this of the Fourier transform of the derivative of the charge can be written as the derivative with respect to the displacement in the unit cell 0 instead of the displacement in the unit cell nu, but looking at the charge at r minus r nu. And then we have this phase. The rest remain the same. But at this point, we can do a change of variable in the integral. This we pose r prime, this r minus r nu. And so the dependence on r nu is given here by this phase factor that was already there, EQR nu, and then a phase factor that comes from the Fourier transform here because we changed the variable in the integral. Okay, what happens is this, that now we can do the sum over all the atom r nu because this derivative of the charge density does not have anymore the unit cell index, and we have just this phase factor that simply is equal to the number of unit cell if q minus k is equal to g, so if k is equal to q plus g, or is equal to 0 in the other cases. So the only term of this Fourier transform that is different from 0 is the term in which k is equal to q plus g. So this means that this function is a phase factor e to the iqr multiplied by a periodic function. And it is this periodic function that we want to calculate with the density functional perturbation theory, because it has to be it is possible, as it has been shown before, it is possible to write this periodic part of the change of the charge density in terms of periodic object. So periodic object that will be determined by solving a linear system, self-consistent linear system, as we can show. So let's start. Well, the block theorem. This is just a reminding of the block theorem. So our wave function are block state in the solid. In the unperturbed case, we have as solutions block function, so that can be indexes by an index k and a valence state v, and have the property that if I do a translation of r nu, I get the phase factor e to the I k r nu and the same block function. Or also that I can write my block function as a phase e to the I k r and a periodic function u k r. Another result that is used later is this, that thanks to time reversal symmetry, the wave function at k is the complex, the wave function at minus k is the complex conjugate of the wave function at k. The block function is due to time reversal symmetry. So if we now write the change of the charge density with respect to the displacement, or with respect to the displacement in one unit cell, it is written in this form. So before we had just the projector and the derivative of the wave function. Now we have to do a sum over all the cells nu, and multiply by this phase factor e to the iqr nu, and divide by the square root of the mass. then multiplied by the wave function, and here we have the complex conjugate of the wave function, the same linear combination of the change of the wave function. So while this change of the block function with respect to a single atom is not really well defined in terms, is an object that is not really well defined, because when we move just one atom, we do not have anymore the block periodicity. So it is clear that if you do not have the block periodicity, operatively it is very difficult to do this derivative. But let's take, so as Stefano has shown, this kind of object can be shown to be a function of a periodic function, that we can call in with an index k plus q to remember the periodicity, and a phase factor. So this object is an object that can be obtained directly by solving a linear system. So to do this, we have to apply another property, however. So if there is time reversal, when we change k with minus k, so we can, here we have a sum over all the k, and so here we can do the sum changing k with minus k. The sum remains exactly the same, and then we can apply what is it? And then we can apply time reversal symmetry. And therefore, this C at minus k is C star at k, and this C star at minus k is C at k. And so this term, it has the same phase factor, so is exactly equal to the second. So these two terms are equal thanks to time reversal symmetry, and we can write this as twice just one of the terms, C star k, for instance, the second is C, and this object that formally we can call is the derivative of the block function with respect to the displacement of one unit cell at the given t. Okay, so one can say that this object must have a phase factor e to the I k plus q. Can guess this because there is a phase factor e to the k r that comes from the fact that this is a block function. And then we have also that this derivative of the periodic function can be treated with the same reasoning. So the translational invariance of the solid can suggest that this has to be a periodic part multiplied by a phase factor e to the iqr, exactly as the charge density or the local potential. And the problem is to calculate this periodic part. Okay. Clearly, if here we have a projection in the conduction bands, but if this object has a phase factor k plus qr, this projection in the conduction band that actually would contain all the vector k prime will just be different from zero only when here we are using the function at k plus q. And so we can define this projection at k prime as a projection in terms of the periodic part of the block functions, and the expression of the change of the charge density will be like this. It will have a periodic part, a projection at k plus q, and then again the block function will be factorized as e to the I kr, and this phase factor cancelled with the phase factor that is in the projector. What remains is a phase factor e to the iqr, and then an object that is lattice periodic if the solution of the linear system is lattice periodic. And so the change of the periodic part of the change of the charge density, that is actually the object that one calculate, is given by this expression. So we have to solve the linear system that will give us the projection in the conduction band multiplied by the periodic part of the block function, and just simply do a product with the periodic part of the block function. This will give us the periodic part of the change of the charge density. Formally, how can we write down an expression for the periodic part of the block function? Well, if we take the expression of so the linear system that is solved to calculate the change of a wave function with respect to an arbitrary perturbation lambda. We sum all these equations with multiplying them by phase factor and divided by the square root of the mass. We will have a system for this change of the wave function with respect to the amplitude of the displacement E1 unit cell at the given Q. And now we can show that, okay, this is already being already shown by Stefano, that if the local potential is e to the iqr multiplied by a periodic part, the charge density will be e to the iqr multiplied by a periodic part, and so the Hartree exchange and correlation will have the same property, and all these phase factor can be factorized. Okay, so let us assume that this Cone-Sham potential has actually this form, a phase factor multiplied by a lattice periodic function. Then all the charge density will have this form, and the right-hand side of the linear system will be like this. So instead of the block function, we will have here just the periodic part that has to be multiplied by the lattice periodic part of the change of the Cone-Sham potential. This object will have a phase, so this in principle starting so from this equation here, there will be no, sorry. Okay. So this will have a phase e to the ikr. This will have a phase e to the iqr. So this object will have a phase e to the iqr multiplied by a lattice periodic function. So in the projection, the conduction band, we will have just to select the projection in k plus q. You have a k plus q, and then the phase factor appear here in front of this expression. The same happens in the quantity that is the solution of the linear system. It can be written as a phase factor e to the iqr multiplied by an object that is the solution of the linear system when we use as an Hamiltonian so this Hamiltonian multiplied by the two phase factor, the one that comes from here, from the solution, and the one that comes from the right hand side. So this Hamiltonian will be lattice periodic, and we have to solve a linear system with this Hamiltonian. The solution will be a lattice periodic object, and the right hand side is a lattice periodic object. Okay, now just one comment. If the change of the charge density, so the change of the charge density will be a phase factor e to the I k r. So the definition of the Cone-Sham potential for a perturbation mu s and beta is this one. So if we again multiply by the phase factor, divide by the square root of the masses, we obtain derivative with respect to the amplitude of the displacement in one unit cell. And if we write that this is e to the IQR multiplied by a periodic function, the same for this, the same for the charge density, and the same for the exchange and correlation part, notice that here I've not used the general expression of Stefano, but just taken the local spin density approximation and okay, assume the a local quantity. So in this case, it is an exchange and correlation potential that is local in the charge density. So we have just to make the derivative with respect to the charge density and calculate the point R. Now, if all this quantity we use the periodicity that we have seen, we can write them as a phase factor multiplied by a periodic part, a phase factor multiplied by a periodic part, or rewrite the periodic parts like this. And this object is the periodic part of the change of the Cone-Sham potential that enters in the right-hand side of the linear system. So in this way, one has shown that by solving linear system in one unit cell, by writing the right-hand side in terms of lattice periodic functions and having a solution that is lattice periodic, we can obtain the lattice periodic part of the change of the charge density, and to set up the self-consistent linear system in just by working in just one unit cell. This, after the self-consistent procedure, will give us as a output the change of the charge density with respect to this phonon perturbation, that is the quantity that has to be integrated in the definition of the dynamical matrix. So the phonon has to solve this system for a given vector q, and for a number of perturbations that are the number of atoms in one unit cell multiplied by 3. And it has to solve this linear system for all these perturbations, or it can do, one could do separately this, each one of these perturbations or a few of these perturbations together. What is convenient is that one does linear combinations that transform according to the irreducible representation, so displacement pattern that transform one into themselves when we do a symmetry operation. This fact simplifies the calculation, because if we do not use this trick, in principle, when you try to symmetrize the response, you mix perturbation.